Okay, so it tells you how many carbons are attached to a certain position. So that's how we're going to identify them. They're primary, secondary, tertiary, and quaternary carbons. So let's draw something out real quick. And I'm going to do it in a line drawing. So, can you find any primary carbons? You guys see some? How many of them are there? Everybody see 5? Okay, these are the 2 obvious ones because they're on the ends. But we also have these guys here, right? So there's 5 primary carbons. How many secondary carbons do I have? Carbons that have 2 other carbons attached. Mm-hmm. So we should see this one, and this one. There are 3 of them, yes? And how about tertiary? How many with tertiary? Close. Just 1. This one's our only tertiary one. And let's see, one more color, both yellow. How many quaternary? Oh yeah, I got 1 left here, so it's got to be your quaternary. Okay. Why do we care? We're going to talk about some reactions that occur, and they only occur on a primary carbon, or they only occur on a tertiary carbon, or they occur faster on a tertiary, or they occur faster on a primary. There are different things that we need to know. Which one is which? Secondary gives us some problems. It likes to be, it goes in 2 different types of reactions. So you need to be able to identify what kind of carbon you have in order to understand what reactions will occur. Okay, so that's one of the things, a small thing that you need to learn. Let's see. So you should be able to do that. Again, you should already know how many bonds should be on each thing. I wanted to talk to you a little bit about the Lewis dot structures with organic chemistry. So let's look at that. So Lewis dot structures with organic chemistry. Generally speaking, we don't do a whole lot of stuff like you did in Gen Chem. It's going to look a little different. So if I tell you that I have this formula, so I have that formula. And I want to figure out what does that Lewis dot structure look like. It would be like a full structural formula, okay, and that's usually what we're going to do is a full structural formula, and we're going to try to figure it out. So we should be able to draw it out real quickly. It is going to be real simple. We're going to have a C, and it's going to have 3 H's on it. Right? I've already kind of told you the order of these. Then it's a C. It's going to have 2 H's on it. So far, these are both correct because I've got 4 bonds on each of the carbons. Well, I need to put one more here. And then it's going to have a C with an H, and then what's going to be hanging off of that carbon? You're going to have another C with 2 H's on it, and another C with 3 H's on it. That's hanging off of it. And then we're going to have a C with 2 hydrogens, and then another C with 2 hydrogens. A little tedious to write these out, I know. And then we're going to have a C with an H. Notice that when I write these, it's always carbon, then hydrogen, then any other element that's attached comes after it, and they come alphabetically. So if there's another element like we have here, we're going to have an oxygen. So we're going to have an oxygen on there. Okay? So is there a problem with what you see there on that structure? That last one does not have the right number of bonds, right? So we're going to have to make an assumption about what's happening here. There's no charge shown on here, so we're not going to have a charged group. What this tells us is that I need to somehow put another bond. Both the oxygen and the carbon need another bond. So what am I going to do? I'm going to put a bond between those 2. I'm going to add one more bond. Okay? So that's your full structural formula. Now, to make it a Lewis dot structure, what do I need to do? I need to have the right number of electrons. How many bonds and electrons, how many groups should be around the oxygen? There should be 4 groups, right? Because it's still going to be an sp3 hybridized substance. It's not a carbon, but it's going to be a sp3 hybridized oxygen. And so I've got 2 bonds already, so how many more pairs of electrons do I need? 2 more. So I'm going to have you use logic to figure out those parts. Does that make sense? Did you have to go through the whole Lewis dot structure like you did back in 112? No. You need to have some good sense of how things come together for organic chemistry. They're very simple in general. Carbon has 4 bonds, hydrogen has 1, bromine has 1, all the halogens are 1. Oxygen is usually 2 bonds and then 2 pairs of electrons. Nitrogen has how many bonds usually? 3, right? So nitrogen is 3 bonds. How many pairs of electrons? 1 lone pair, right? So that's the common thing that we see. Oxygen, we just said, was 2 bonds, 2 pair. So those are what we commonly see, okay? Any questions on that? Okay. What if I had done the same thing? I'm going to make it a little bit smaller, and we're going to make it kind of a simple one, okay? And you could have seen it this way. I'm just going to write it a different way. Okay, so I put a negative charge on there. What does that mean I have? I have more electrons, right? That means I have extra electrons. You should know electrons are negative, so that's not hard. So we know we're going to have extra electrons on here. Let's see if we can figure out where they belong and how we can do it. Now, these two are the same, right? They're just written 2 different ways. How are those 2 the same? What 2 things are being the same? So you see this pair here? That is this and this, just rewritten together to make them look like a branch, right? So it looks a little different, but they are the same formula. I'm going to go ahead and write it as we see it. So C, and I'm going to keep it kind of together this way, CH3, and then I'm going to write this one separate so you can see it, and then CH3. And I'm simplifying this. This is not really a full structural formula. It's also not a condensed structural formula. So this is condensed, right, because it's all in one line. This is not full because I didn't take all the H's and spread them out. The reason I didn't do that is because they're not really the important part here. So oftentimes when you're drawing these things, you'll see I get kind of lazy and I don't draw everything out. I focus on what's important, and so that part is drawn out. Does that make sense? Okay, so now we look at that carbon. Does it have the right number of bonds? Does the carbon in the middle, just that focused one, does it have the right number of bonds? That one seems to be fine. It's okay. It's got its octet, right? These 3 hydrogens are attached to that carbon. You can't see where I'm pointing. I apologize. These 3 hydrogens are attached to this carbon, even though it's written carbon. Remember, it's always carbon, then hydrogen, then anything else that's attached, okay? So here we have this oxygen. What are we going to do with that? It can't make a double bond because the carbon already has enough bonds on it. What's it going to do?
There's the extra electron.
So first we're going to put in our pair of electrons that we should have had. So we know we should have 2 pair, right? Now, do I just add 1 electron in to get a negative charge? I have to add 2. And why is it? Well, originally we had a bond to a hydrogen there probably. Now I've taken that away and I've left behind 1 of the electrons, not both, but I had 1 originally there. So this is our thing, and now it's going to look like that. That is its formal charge. The formal charge on this is -1. Okay? Let's try another one with a positive charge, just so you can see how to get that in time. I tend to move things fast. I apologize. Pretty good? Okay, let's do a formal charge, positive charge. Which position has the charge on it? Can you tell? Number 2 has it. How do I know? It doesn't have enough bonds. So just looking at it quickly, hopefully, you can see that that's missing something, right? If you were to draw this out, you'd say, okay, I got a CH3, a C, it's got 1 H on it, a CH2, and a CH3. And I know that's kind of drawn simply, but if you put all the hydrogens around everything, you can say this guy's got 4, This one's got 4, 1, 2, 3, 4. This one's got 4 because we got 3 hydrogens and another one. This one's missing something. So how do I indicate that it's missing something but still has it? We're going to put a positive charge on that. That's called a carbocation. It has a formal charge. Is equal to plus 1. Okay? Any questions on that? Let me flip over to the, okay, so we look at forces. They start with, well, you already know covalent and ionic, right? So if you were going through the whole list, then you would have ion dipole. I think you guys have all seen these, right? Then hydrogen bond. Then dipole-dipole. Then dipole-induced dipole. So that's a long name. And then London forces. Have you seen all of those before? Anybody not seen some of them? So some people may not have heard of dipole-induced dipole, and they may not have seen ion dipole. Sometimes people don't talk about those. So those two are only for mixtures, so we don't usually talk about them as boiling point type of things because it's a mixture. So I'm going to eliminate them for the moment, but it does tell us, and just so you know, this means that something is ionic with something polar. So that's how we know it has to be a mixture, because it has two different things. And this one down here says it's polar because it says dipole, and an induced dipole means it's nonpolar. Again, a mixture. Okay. So what things do we have? I'm separating these guys because these two are not interparticle forces, they're intraparticle, right? So they're within. Is this all coming back to you a little bit? You guys remember them? Yes? Okay, so this is in order of strength. The more polar something is, the more stronger its bonds are going to be. Because when it's polar, it has kind of close to being an ion. You guys know opposites attract, right? We already know positive goes to negative. When something's polar, what does it look like? When it's polar, something like this, we're going to see a positive and a negative end. I'm going to put little deltas on there to say that the two ends are a little bit different from each other. One end is positive, one is negative. I'm going to ask you guys, does anybody know how I knew that the carbon was more positive than the oxygen? Besides the fact that I've done it millions of times. Other than that, any ideas? Electronegativity, yep. So if you're given a choice, we're going to talk later about resonance structures. If you're given a choice, which one should be more negative is the one that is more electronegative. Does that make sense? So we're just looking at polarity. It's going to have more negative charge on the thing that is more electronegative. You should know those trends from the periodic table, right? If you look at a quick periodic table, put my hydrogen and helium on. We ignore the last one. We know that electronegativity goes up to this corner. What's the most electronegative one? Most electronegative element? Fluorine. Fluorine, yeah, you guys should know that one from way, way long ago, right? So we have the most electronegative is fluorine. We really are only concentrating on the top corner because we're looking at schnapps, which I always call schnapps is an alcohol, right? But we're going to say just carbon, hydrogen, nitrogen, oxygen, fluorine, phosphorus, sulfur. Those are kind of the things that we're looking at. We also do bromine and iodine. I don't need you to know real details what those electronegativities are, just which would be a little bit more electronegative. So you should know the trends. If you know that fluorine is the most electronegative, and then I say which is more electronegative, chlorine or iodine, could you tell me? Chlorine, because it's closer to the top, right? So you should be able to know that trend. You should know carbon versus oxygen, nitrogen versus oxygen. Very easy because we know that trend going across, yes? I'm not going to ask you is, let's see, oxygen or phosphorus I could ask because they both go the same direction. Oxygen should be more electronegative. But what about nitrogen and sulfur? I won't ask you that because it's hard to tell. You'd have to actually know the numbers to know. You won't see it from a trend. Does that make sense? Because one says it's going up, the other one says it's going down. Does that make sense? So with those we should know. When we talk about polarity, we're going to look at this guy is polar, right? So this is a polar compound. So what types of interactions could it have? Well, we can look on here. It has anything that says the word dipole. Well, this doesn't say it, but it could be there. So anywhere you see dipole, it could be one of those interactions. Does it have London forces? Yes, everything has London forces, right? So when they talk about what is the strongest force present, that's what we're usually looking for. All the lower ones are usually there, but we're looking for the strongest one. Okay, we always say, what's the strongest force possible? Could this one do hydrogen bonding? What do you need to have hydrogen bonding? Gotta have hydrogen, that's a start. Do we have hydrogen here? Yeah, we have hydrogen, but it has to be on what? Exactly. So we have to have hydrogen on the phone, fluorine, oxygen, or nitrogen. That's how I remember it, it's phone. Fluorine, oxygen, or nitrogen tells you that it's going to have hydrogen bonding. Now, hydrogen on sulfur is really close to hydrogen on oxygen. It's similar, it's not quite as strong. Is it very, very polar? Yeah, it's going to be very polar, but not quite as much as what we see with hydrogen on fluorine, oxygen, or nitrogen. We do not have hydrogen on fluorine, oxygen, or nitrogen here. We have it on carbon, so that one is not going to be able to hydrogen bond. So we know it doesn't have this, okay? If I were to look at this compound and say, what's it with, and if I just asked you if it was with another particle of the same substance, that's when we're looking at boiling points, is we're looking at two of the same thing, not a mixture, okay? So both of these are polar. That tells us that this, let's see if we can get another color here, is going to be your answer. It's going to be a dipole-dipole because both of them are polar, right? So two polar substances, that means that this substance is going to be a dipole-dipole interaction. How does that compare to something that hydrogen bonds? Is it going to have a higher boiling point or a lower boiling point? It's going to have a lower boiling point than something that can hydrogen bond. So for instance, if I were to ask you, which has a higher boiling point? Could you tell me? They have the same molar mass, right? I don't know if you can tell. Same number of carbons, same number of hydrogens, same number of oxygens, the same molar mass. Can you tell? You should be able to do it without even drawing it out, because it's kind of drawn for you there. So A or B, what do you guys think? Higher. Yeah, this is higher because it can hydrogen bond. This one is going to have dipole-dipole. Okay? And some people will look at it and say, well, why is it polar when it has two ends that are the same, right? Do you know why it's polar? It has two ends that are the same, so we'd say, oh, maybe the two ends are going to cross out like we did way back in prep chem. The two ends canceled out with CO2, right? And became nonpolar. You remember that? Kind of maybe. So this guy's nonpolar. Why is this one polar? What's that? The lone pairs, yeah. So think of this like water. You've done water before. You all know it's bent and you know it's polar, right? This is going to be the same thing, but now we're going to just change it to an ether, and it's still going to be bent with its lone pair electrons. Did I have to draw them in? Could you see that it would be that way? Think of water and make a comparison with these types of things, right? What kind of bonding does oxygen have? You should be able to see that this is going to be a bent shape. Think of it as water. If I put a whole bunch more carbons on here, let's just make it really wiggly here, you would still know it's going to be bent shape. Doesn't matter how many carbons I put there, where that oxygen is, it's going to be bent. Everybody doing good so far with shapes and things like that? Kind of, maybe? Okay. What else did we have that we needed? I'm just refreshing your minds on things you've heard, hopefully, before. Let's see. Then we have functional groups next. Actually, I wanted to talk to you a little bit of hybridization. I know we talked a little before. Do you know what's happening when something gets hybridized from Gen Chem? What you're looking at, really? Not quite? Okay, let me talk to you. about atomic orbitals first. We look at carbon. And how many electrons do we look at with carbon? How many are there? 6 electrons, 4 valence electrons. You're right. So we're going to have the first 2 are in the 1s orbitals, right? The next ones are in the 2s. And then we have the 2p's. So we have 6 total electrons, and that should be its atomic orbital, right? That all makes sense to everybody so far? If I were to bond to this, what would you think is going to happen, just looking at just this? How many places would you bond normally? You would say, oh, sorry. You have this spot and this spot. That spot. Those are 2 places you could bond, right? Or do you just get 2 bonds with carbon? We know that doesn't happen, right? So what does happen? Well, some people would say, well, okay, maybe I excite one of the electrons. Remember that? When we excite an electron, so we're going to take this guy. I don't know if I can move it or not, but we'll take it, see if I can move it like that. No. I'm going to take that one, erase it from there, and add it up here. So now it's excited. If I did that, what would I get? I got 4 bonds. Are they all equal? So this would give me 4 unequal bonds. How do I know that they're unequal? This is to an s, and these are to the p's. So those are not going to be the same. What is the shape of an s orbital? These are the only shapes you got to know. There's only 2 of them. It's a sphere, which I can't ever draw. That's a sphere. As good as you're going to get from me. And the p orbital is like that, right? That's a simple. It looks like an 8, or it looks like an infinity sign, one or the other. I'm not as precise as they are in 112. You get the basic picture, and I'm happy with you, okay? You draw that, you're okay. What's the third direction? It's that z direction, right? Well, I'm horrible at those, but it's laying like that. So that means it's coming towards you, yes? So we have the vertical, which we call the x. This way is our y, and our z is coming forward. And one of the ways that we show that something's coming forward is we bold it, and that something's going back is we make dashes that's like fading away, if that makes sense. And so that's our z direction, x, y, and z. So we have a 2p x, y, and z, right? So those are different bonds. When it bonds to something else, we need to know what kind of bond is it having. So you may have seen these types of bonds. So if I have, let me go to another page. If I have a sigma, this s orbital, overlapping with another guy that has an s orbital, these 2 interact here. That is what we call a sigma bond, right? If I have a p orbital like this, and it overlaps with another s orbital like this, that is still going to be a sigma bond. We don't see a whole lot of that in here, okay? That's still a sigma bond. But if I have a p orbital, and it interacts with another guy, and these 2 interact in this way, where their p orbitals are actually interacting with each other in the same way. Notice that the p orbital is interacting in 2 different places. This is called a pi bond, okay? That's what we see for our double bond. When we have a double bond, we have a sigma overlap and we have a pi overlap. You have to have both. So the first one's a sigma bond, the second one's a pi bond, okay? The pi bond is above and below the carbons, not between the carbons, but above and below, okay? Any questions on that? Okay, so now we're going to go back. Formal charges. I'm sorry, did you going to go back and we'll go forward? So we had our 1s. We ignore our 1s because they don't do anything, right? It's just the valence shell electrons that we have to worry about. And our 2p's, and we had this. So we excited it. We were at the excited state. Now we're going to blend those together. So when they blend, where do they blend to? Well, what you're going to see is that you're going to get 1 of the s orbitals and 3 of the p orbitals. This is for an sp3 blend, an sp3. Good, doing good so far? How much energy does this have? Has it lowered in energy? Has it stayed the same? What do you guys think? The energy is pretty much the same, right? So where is it? If I were to just make a graphic here and say this is at 0 and this is at the number 1, okay, so the energy difference between them is 1, and those are not real numbers, so just kind of give you an idea. where would this be located compared to where it started? Where would it be on that? So let me just give you a, this is 0.5, 0.25, 0.75. Where do you think it'll be? It'll be at 0.75. Why? Not a trick question. It seems hard, but it's not. If you look at how many S's you have and how many P's you have one S and 3 P's, right? That means you have a total of 4 orbitals being blended together. It is 3/4 P, yes? And it's 1/4 S. This blend is going to be there. So it's going to be at the 3/4 point. I didn't do a very good job of lining that up, but it's going to be at the 3/4 point. Does that make sense? 3/4 of the energy, because we've lowered 3 of them by a little bit and we've raised 1 up by a lot. Yes? Still the same total overall energy. Yes? Everybody okay? Okay. So that is now a hybrid. This is our hybrid orbital. And I've got still 4 electrons. 1, 2, 3, 4. Can you tell the difference between them? They're all the same now, right? So when we bond to carbon, all 4 of them are going to be the same electronically and energetically. They're all going to be the same because they all have this hybrid orbital overlap. What is the shape of the hybrid orbital? It's a tricky one. So originally was like this and like this. We're going to blend those 2 together, right? It ends up that if you had, and here's your carbon in the middle. Sorry, let me draw the carbon in another color. Carbon here and a carbon here, right? We put them together, and this orbital is going to be, if I blend these 2, it's going to be carbon here. Still going to have a little bit of a nub, but it's going to have a whole lot of one going one direction, right? It ends up that all 4 of them do the same thing, so that when you look at the carbon, it has, I'm not good at drawing these. So this nub goes with that nub, this nub goes with that nub, this one goes with that one, and I don't know, I must have missed one somewhere in there. But they each kind of have 2 nodes. The little tiny node we ignore. We're going to really just ignore that. We're just looking at the big balls coming off of it. What is the shape of that? You guys already know the shape. When you get an sp3, what's the shape? Tetrahedral, right? So this is our tetrahedral shape. That's where the tetrahedral shape comes from. Because all 4 of them are equal, they have to be as far apart from each other as they can. They push each other away, and the best way for them to do that is to have the 3 hydrogen, or the three of the things sticking down and the 4th one sticking up, but they're all equally spaced out, right? So nothing's planar in this section. What happens when you do an sp hybrid? What are you hybridizing? So let's look at that. I'm going to ignore the 1s part because we're okay with that. Everybody okay with that? So we're going to have the 2 s's and 3 p's. So we're just looking at those 4, right? We excite 1 up. Great, we got that. But we want to make the hybrid. Sorry, this is not erasing well. We want to make the hybrid, and we're going to only hybridize 2 of the p orbitals instead of 3. What do we get for structure? What do you see? One of them is going to be still a 2p. 3 of them are going to be the hybrid. What is the hybrid going to be called? sp2. There are going to be 2 sp2 because we're on the level of 2. Yes? Any questions? So I've got 3 orbitals there. Now I'm going to put in my electrons. I still have 4 electrons, right? What do I do with the bonding? What kind of bonding do I have? These 3 are going to form sigma bonds. This one is going to give you a pi bond because it's still a p orbital. And p orbitals have this, and so they can still bond above and below. Does that make sense? The other 3 are going to be just your regular sp2 hybrid, which is big ball on one side, little ball on the other side. Okay? So they're still going to have that same thing in 3 different directions, those are going to be planar still, right? We talked about trigonal planar last time, so you kind of know what the shape is. So when this bonds, these three are going to be as far apart as they can be, 120 degrees, right, because it's in a plane. This one is going to be above and below the plane. It could be in front of and behind the plane. It could be on either side of the plane, right? So it can stay in any of the three directions. I almost always draw it above and below because it's the easiest one to draw. The up and down is easy for me to draw. So you're going to see me doing it all the time, up and down. Officially, it could be in front and behind, but those are a bear to draw. And going that way is really bad. So I always do it the up and down. Okay, any questions on that? Okay. And then what energy level would the sp2 be hybrid orbitals be at? What number would they be at? What I mean by that, let me rephrase the question. If this is 0 and this is 1, where will this be? What number will that be at energetically? So how many of them are blended? Just 3, yes? How many of them are p orbitals? 2. So it's going to be at 2/3 of the height of the p orbital, which is the number 66, 0.66, right? So if you were to guess where this is, you would say, oh, this is around 0.66. Not at a half, it's going to be around 0.66. Okay? Any questions on that? I got one more question for you that's related to that and the previous question, because it's going to talk about bond strength. We're going to talk about bond strength a little bit later. Which one has more S character? Okay, so we're going to talk about percent S character. And so if I look, actually, let's go to one page. sp2 versus sp3. So sp3 versus sp2, sorry. Which one has more S character? So this is 1/3 S. This one is 1/4 S, yes? Which one has more S character? More S. Okay. Why do I care? Well, the S shape puts the electrons really close to the center. The P shape has them sticking out. So which one is closer to the carbon? More S or less S? When I blend them together, it's going to have more S character, more of this, so it's going to be closer to carbon. Nucleus. It's closer to the nucleus. Is that good or bad energetically? To be closer to the nucleus. Well, look at this question then. Let me do it this way. These are my p orbitals. This is my s orbital. Which one's more stable, S or P? Can you tell on an energy diagram? You guys know this. So we know this is the lowest energy down here, right? S is more stable. Why is it more stable? The electrons are closer to the nucleus. So which one do you think is a more stable hybrid, sp3 or sp2? sp2, because these bonds are closer to the nucleus. Now, it still has the p orbital, so it's not necessarily energetically any better, because it still has that last p orbital. But we're looking at the bonding, we're going to see that those electrons are closer to the atom. So if we try to break it apart, we're going to see a different bond strength because of that, okay? I want to ask you, which is stronger, or sp2 or sp? So which one do you think has more S character? What's that?
What is S character?
What is S character? It means how much of it is like an S orbital. So it's a blend of S and P's. So the more S it looks like, the closer it is to being a ball. So if you were to look, just real quickly, if you were to look at an sp3 orbital, it looks kind of like this. An sp2, not good at drawing these huge differences, looks a little more like that. And an sp orbital, all right, come on. I gotta get it around the same size. They're about the same size, but they're a lot more like fatter. Sorry. They get closer and closer to the nucleus. Does that make sense? So they're scrunching down, they're more like a ball. And the more S character it has, the closer it is to the nucleus. Okay? Is that stabilizing or destabilizing? That stabilizes it, right? Okay, so the sp is very stabilized by pulling those electrons in. It still has the p orbital, so it hasn't changed the overall energy, but that sp is very strong. The sp orbital, where it bonds, is going to be strong. And that's your sigma bond. Not the pi bonds, but the sigma bonds are going to be stabilized by having this. Okay. If I were to have a negative charge, so I have a pair of electrons on all of these, which one would be the most stable? I have extra electrons. Do they want to be close to or far from the positive nucleus? What do you think? Do electrons like positives? Or do they hate positives? They love positives, right? Opposites attract. You guys have heard that forever. You didn't know it had to do with this kind of chemistry, but we're talking about chemistry. Opposites attract. Those negatives love the positives. They're going to try to get as close as they can. So which of these is going to be the most stable? The one with a negative charge? The sp3 hybrid, the sp2 hybrid, or the sp hybrid? Yep, this is our most stable anion. We're going to talk later about how that makes alkynes very acidic, fairly acidic, not very acidic, fairly acidic. They're not like HCl, I promise, they're nothing like that. But for an organic compound, they're fairly stable. Most stable anion, because the electrons are close. Okay, does that make sense? I'm doing that time, I only run too long. Got lots of time. Okay, does that make sense on some of the hybridization stuff? I don't have any stuff on here about hybridization. That's why I wanted to talk to you a little bit about it, because you're supposed to know it, but I'm getting the sense that there wasn't a strong, great knowledge of hybridization. So I wanted to show you what we look at with organic chemistry. Again, the video will do the basics, but I just want to do the things that are a little bit more challenging. So butyl is one of our more common ones, so you're going to see this. What's that? Well, that's tricky, isn't it? Sorry. Switch that over again. Okay, so naming alkyl groups. So butyl is a really common one because we use it a lot. So you have seen, well, let's do iso first. Isopropyl, you guys all know what that is, right? Everybody heard of that one? Because that's the one that most people talk about. Iso means a branch, CH3, at the end. Okay, so it's a branch at the end. So isopropyl is a 3-carbon thing, and maybe I have an alcohol or something like that, right? So it's got a 3-carbon branched thing. If I have a long carbon chain, and coming off of that long carbon chain, I have 3 carbons and it's joined at the middle, that's isopropyl, okay? If I have a 3-carbon chain like that, without it being branched, that's propyl. Okay? If I want to look at propyl alcohol, this would be propyl alcohol. That's a common name, not an official name. And this one would be isopropyl alcohol, which is also known as rubbing alcohol, but nobody ever calls it that in here. We do use isopropyl alcohol a lot, so don't get surprised when you see that one. But it means that the OH is in the middle versus on the end, okay? Questions on that? Okay, let's try butyls. Butyls are really common. So butyl means 4 carbons, right? So if I have a long carbon chain, and I have, 1, 2, 3, 4 carbons coming off, we would just say that's butyl. If I have 4 carbons coming off, and it's at the end, we would call that, let me do this, this is my 4 carbons, I apologize. Notice how there's a branch here at the end? That is isobutyl. Okay? If I have the 4 carbons and it's here on the second carbon, we call that sec-butyl. Again, these are common names, so they're not things that you probably have heard before. It's a branching pattern that we see, and this is something coming off of something else. So you're seeing it coming off of a main chain. You could also have an OH on here, and it would still be sec-butyl. Yes?
Would it be the same thing as 2-butyl?
What's that?
Would it be the same thing as 2-butyl?
No, not necessarily, because 2-butyl would mean that the butyl is hanging off of carbon number 2. So you're saying as a branch, you could also have another name for it? Yes, I'm sorry, yes. So the other name, you're right, I think I know what you're asking. The organic naming for this would be, it has 1, 2, 3, right? So that would be a propyl, and it has a methyl group hanging off of it. So that's a methyl propyl, and it's off of carbon number 1, so it'd be 1-methyl propyl is the organic name for that branch. That's the real IUPAC name of it. It's a lot harder than sec-butyl. So most people use sec. Okay, so the sec-butyl is the common name. The other one is its branched name. Whereas this one would just be just butyl in either case, it doesn't matter, because it's the branch, right? This one would become 1, 2, 3, right? So with 3, sorry, let me do that in the other color. 3 carbons on the main chain, so that's still going to be propyl. It's going to have a branch, that's this guy here, that's a methyl. Which carbon is it on? On here, that is going to be on carbon 2, so that's 2-methyl propyl. Okay, everybody see it okay? This is coming off as a branch coming off of the main chain. So let's say this was a decane or something like that, 10 carbons long, okay? So if the blue part is decane, the name would come out with butyl, sec-butyl, and isobutyl, or it would come out with butyl, 1-methyl propyl, and 2-methyl propyl. Those would be the 2 different ways we would name it. Let me add one more to it, and then we can finish this off. Let's add this guy here, which looks like this. It's also 4 carbons, okay? So we can count the 4 carbons. If we do it like this, the longest chain is 2 carbons, right? Its common name is going to be T-butyl. Everybody calls it T-butyl, but it's also tert-butyl. I don't know anybody that says tert anymore. Pretty much everybody says T-butyl, but tert-butyl means T-butyl. They mean the same thing. So tert-butyl or T-butyl. What would it be in its correct IUPAC name? Now we're going to look at the full length of it. How long is the main carbon chain? We'll make this our main chain. How long is that? 2 carbons, everybody see it? So 1 hanging off, the second one coming off in one direction. I don't care which direction because they're all the same. So 2 carbons, how do I name that? 2 carbons is? Thank you. I know you know that. Okay, and then we've got 2 branches coming off. They're both 1 carbon long. So those are methyl. And there's 2 of them, so we're going to put in dye. I'm going to do a different color. Let me see. You can't see it? I don't know how to make it shrink for me. Let's see if I can get. I don't know why it doesn't show. There we go. How's that? There we go. So that's a dimethyl ethyl. And what numbers are they on? Which carbon number are they on? So if this is our 1 and 2, what number are they on? They're both on 2. So this would be a 2,2-dimethyl ethyl. Okay, so this is a side group to our decane. Okay? I'm going to put it all together into one long name. I wasn't going to do this is kind of a long one, but I'll show you the 2 different naming systems, and they come out with different names. So, yes? 1-1, I am sorry, because I'm wrong. That's a good reason, right? 1-1, thank you. Let's make that 1-1. Thank you for asking. 1-1. Okay, everybody good? Okay, if it were a longer chain, so it was pentyl, say I had a bend in it, then it could be on 2-2. The T is at the end usually of whatever group it is. So that's kind of how they're named. Let's see. Let's see how you would name this whole thing. I don't know if I can shrink it all at once. I don't think I can. Oh, I'm going to die before we go. So we know it's a decane. What are the different groups that we had? So I'm going to go ahead and write them all down. So the first one we had in the non-IUPAC name. You guys know what IUPAC stands for? Do you guys know what IUPAC stands for? Know why I say that word? All right, let me go back one step. IUPAC is International Union of Pure and Applied Chemists. You don't need to know that, but what you do need to know is that is the official naming system that is the correct way to name things. The common names are the sec-butyl, T-butyl, N-butyl, or butyl. So the butyl can sometimes be called N-butyl, and the N stands for normal, unbranched, no chain, no branches. So all of those iso, T-butyl, those types of things are all common names. They are not the official way to name things, but you see them all over the place. So you see them in books and things like that. So I just want you to kind of recognize them. Once in a while, they might say, I got T-butyl chloride or something. In lab, you'll see some things with bottles that are labeled that way because it's so much easier and shorter way to say it, right? So it doesn't have all this branching 1,1-dimethyl-benzyl-butyl, which is bad. Okay, so let's go ahead and name them. So of the ones that are, I'm hoping I can last through this, that we had, one of them was butyl,